Hey guys, it's Mr. Fourth Dimension. Welcome to another episode of the Geo Project. So last time we were doing some spatial rotations and we just got that started so that we can do segment collision. Let's find that code. I want to take a quick moment to look and see, we've got 300 lines done so far. That's okay. Only doing 15-minute chunks makes it kind of hard to really speed through the code, plus I've been super thoroughly testing. But anyway, I've just been curious about how quick we've been getting stuff done. Let's get on to it. So the problem we left off with was we were in the middle of rotating the entire space around. And before we do the rotation, there's something else we want to do, because we want to center the rotation around P1. If we don't, it'll still work. We can rotate all of these points, all 4 of these points, by the rotation factor, but then we're doing 4 rotations instead of 3. It's easier to adjust all of the points to put this at the origin first, and then to do the rotation on the 3 remaining points. So, step 1 is going to be to center Q2, or P2, Q1, and Q2 around P1, so that P1 is more like the origin. So we'll call this new set of points. Well, you know what? We'll just make the changes directly to the points this time. So Q2 is going to become, well, I said last time we would start with operators, and we probably should do that. So let's put a break on finishing spatial rotation and come up here and do some quick operators. So I'd like to do an operator for addition and subtraction, which will look, excuse me, which look like this: A, B, and that'll just return A dot x plus B dot x, A dot y plus B dot y. Do the same thing here with minuses. A dot x minus B dot x, A dot y minus B dot y. That's fine. Now the next one we'll do is we'll do a times, but when you do multiplication, you're not going to multiply 2 vectors together. I mean, you can, but there's multiple ways of defining vector multiplication, right? You can do dot products. You can't do cross products in 3D. You can do element or element-wise or Hadamard multiplication. So we're not going to do vector times vector, just because we don't want there to be any ambiguity in terms of which one that is. But we will provide little functions for those things. And we also, what I want to do, I'm not going to provide a divide, because the trick with these is you have to do them on both sides to do this correctly, right? Because sometimes I might want to multiply before and after, just for notational convenience, and then I would have to do it. A divide would always come after, and it just makes more sense to multiply by the 0.5 instead of dividing by 2 and stuff like that. If that turns out to be wrong, and we need to divide, it's easy to add, so not a big deal. The other thing we want is we might want plus equals operators and stuff like that, and this will be probably the only time I ever use a reference in C++ is to make the syntax for this work. Because with these, you're actually trying to change one of the operands, and you want to return a reference to that, and there's just no way to do this. I mean, you could do it with pointers, but then you're you have to address things when you add them together, which is not what you want. So I just use references as sparingly as possible to make operators work in this case. And then this is just a matter of A dot x plus equals B dot x, A dot y plus equals B dot y, and then return A. And then the same thing with minuses. And I think we won't do one for times. Well, at some point I'm going to think that there's one for times, so I'll do one for times. It is defined a little differently, but I think that's okay. So this is float k, and this is just times k times k. Alright, so that was one of the things I said we would take a sidebar to do. I'm not going to take the time to test these because if there's bugs in these, it'll come out right away, and they're so trivial that there probably aren't bugs. It will take a minute to make sure that it compiles. Interesting. Okay, right, that's just warning me that I haven't finished everything I need to do here. But before we do that, I said I wanted to do these, so let's switch over now to the math. I always do Control B to open buffer sort of thing. Let's switch over here and let's expand upon this system a little bit. So first thing I want to do is I want to make a global const real32 pi 32, which will be this, which is just to say it's a 32-bit version, and then this will just be pi 32, and then maybe in the future if we want a 64-bit version we can define that. Well, I'm thinking now that I say that and look at it, it's going to conflict with what we're going to do next, so we're actually not going to do that. Maybe I'll think of a different way of doing real 64s later, but right now we're not supporting those at all anyway. So the next question is, how do we represent like half pi and 2 pi? So it could be pi half like this, I could write half pi, I could write pi over 2, then the question is what is 2 pi and stuff like this. I think what we might do is we might say that this is like pi over 2, pi 1/2. Yeah, that's what we'll do. So this will be pi times 2, and then this one will be global const real32 pi 1/2 is pi times 0.5. We'll also grab pi 1/4, which will equal pi times 0.25, and then let's take pi 1/3, which will equal pi divided by 3. The reason I do a divide here rather than 0.3 is if I do this, I guess I could do it this way. It's just I have to list out enough 6s to be sure that I've gotten all of the 9 decimal points is normally enough for a float if I remember correctly. Actually, 6 is like the number it can have, but just to prevent like weird rounding stuff, it doesn't hurt to go a little farther than you can actually store in a float, because the compiler will just turn this into the correct number. So I guess that's the right way to do it. That's 2 pi. We don't really need more than 2 pi to be a constant. So I think that those are good. And then the other more important part of this is roots, right? We want, let's grab a calculator. Let's take the square root of 2. 1.4142. So we'll say square root. No, what is the square root? That's it. Square root of 2 equals 1.414213f. Let's do that for a few, because square root of 2 is useful, square root of 3 is useful. 1.732. Whoops. No, come on, just move me over to the calculator. 1.732051. Alright, so that, I think, is what we need for those constants. Other square roots don't come up as much. These are pretty important in trig because they do the special triangles that come up from time to time, which we can use to test, and also possibly they might come up in algorithms at some point when we encounter those triangles. But anyway, that should be all we need for that. Is there any other to-dos like that? Okay, Okay, that's not the same kind of to do. Okay. So let's get back to rotating this. Like I said, the first thing we want to do is we want to adjust all other points like this. And now we can just do it this way. P1, Q1 minus equals P1, Q2 minus equals P1. So now we've centered P1 in the center, and we have the angle from Q1 to Q2, which is stored in theta, and then d theta is how much we want to rotate by, and then these are the sine of d theta and the cosine of d theta. So next what we need to do is the actual rotation, and the way you rotate a point, if you want to rotate a point around the origin, what you do is you say something like this, right? So I gotta store these in extra points, so I'm gonna make a temp, or even better yet, we'll just make a rotated, like a P2 rotated, and then a Q1 rotated, we'll put an underscore there, and the Q2 rotated. P2 rotated equals, well, dot x equals P2 dot x, and then you multiply this by the cosine. This is just a formula that I have memorized at this point. P2 dot y times the sine of how much you want to rotate. So you take, basically what you're doing is you're taking the angle you want to rotate by, and you're using the cosine of it and the sine of it, and you're multiplying that by the correct numbers here to do the rotation. And I'm going to skip the math on that because I already know it, and normally when I do the math on here, it's because I'm thinking it through, and this is, like I said, just a formula that I have memorized. If you want to see that it's correct, you can do it out on paper, and if you know trig, of course, figure it out. Or if you want me to, well, that shouldn't be an x. So then the formula for x after the rotation is it's x times the cosine plus y times the sine, and the formula for y is y times the sine, y equals negative x times the sine plus y times the cosine. That does a rotation. And then we're going to compute rotation for all 3 points. Now you can see here why rotating a point is not the cheapest thing in the world. It's not like going to kill us because it's what, 1, 2, 3, 4, 5, 6, 7 operations to do this. Not to mention these 2 assignments, maybe 8 or 9 operations to rotate a point and store it. And of course we had to do 1 sine and 1 cosine up here to do all that. So we're not doing tons of sines or anything. We're doing 1 sine and 1 cosine, but we're still doing a lot of this. Maybe we can find a way later to do segment collision that won't rely on the vertical system and like the vertical segment collision, and instead we won't, and that way we can get rid of the rotation. But then of course whatever we come up with has to be faster, so much faster than the vertical segment collision that it's worth the extra work. Like, no, it doesn't have to be faster. So what am I trying to say? I'm trying to say it's got to be faster than this rotation. Otherwise this rotation is still worth it, right? The rotation plus the vertical segment system is just what we're using now. So if we come up with something different, we'll have to time it and see if we actually make a win on that, because maybe the rotation is actually not as slow as whatever we come up with, or maybe what we come up with is faster. Anyway, we have these points now, and now we're going to just call geosegment, no, that's the wrong one, segment vertical collision. And why is this saying it's going to return real 32? That's silly. This should be returning geocast result, right? And it's going to treat P1, P2 as the ray, and Q1, Q2 as the segment that it's casting against. So this is the one we're getting T information for, because this is the one we made vertical. So to call this, we need to tell it we need to tell it P1, we need to tell it P2. So there's a little bit of waste here. So we might want to clean this up now that we've figured out once we debug this and see if it's working. The waste is that our vertical collision system assumes that P1 isn't centered and then centers these numbers to it. But now we've discovered we actually need to center the numbers here in order to do the rotation. So what we want to do now is go back and clean these up so that they don't have do not center around P1 in the vertical line code. So that'll be the next thing we have to do. But we can get this algorithm written and tested before we do that. Well, we can't test it this time, but we can get it written and test it next time. Rotated, and then we need, let's see, top, bottom, and middle. So the top is, we rotated it so that Q2 should be the top, I believe, right? From Q1 to Q2. Yeah, I think that's right. So Q2.y down to Q1.y. And what's the x? Well, we can take either one of their x's. So there's a little waste there because they both have the correct x, which means maybe we don't need to compute the x for one of these. Because if the math is right, they should both get the same x, so there's no point in rotating both of them correctly. But anyway, let's just finish this off by returning this, and next time we will test this and make sure things are working, and then we'll go through and clean it up if we have time, or we'll do it the next day. Let me finish this to-do real quick. So to-do, do we really need to rotate the x-coordinate twice if it will always be the same for Q1 and Q2? Alright, see you guys next time.